Hello again. We're now moving to a new frame of analysis. In the first two modules, we looked at the points as such. In the first module, we used statistical approaches towards point pattern analysis. And in the second module, we used more of a machine learning perspective to look at clusters and points. Now we move away from the points themselves, but put them in perspective relative to what is called the population at risk, and we focus in this module on clustering rates or proportions. In the first set of slides, I talk about the concept of a rate and how we make maps for rates, and specifically how we use smoothing to make those maps. In the second set of slides, I will discuss a special form of the local Moran statistic, which is corrected for use with rates or proportions. And in the third set of slides, I talk about scan statistics, which have been specifically developed to deal with clusters of rates. So in this first set of slides, I start by clarifying the concept of risk and rates, then define excess risk and excess risk maps, discuss a little more technical the issue of variance instability in rates, and then finally how we use smoothing to correct for this instability. Risk is a complex concept. It has many meanings in many different contexts. Here we will use the notion that risk is the probability that an event may occur. But we don't actually observe the risk. We do observe events, and of course we can think of these events as being generated by a risk surface, but the risk itself is unobserved. So our objective here is to obtain an estimate of the risk, and then specifically in a spatial context, to map this estimate of risk at different locations to assess the extent to which it's homogeneous or heterogeneous over space. So rates are estimates of risk, and we move from counts of events, which, as I referred to earlier, is a spatially extensive variable in the sense that the larger the area, the larger the number of counts one could expect. And we move from these counts to rates or proportions, which are a spatially intensive variable in the sense that it's corrected for the size of the population. So the rate is very simply the ratio of the number of events over the population, more specifically the population at risk. So if you recall our early example of car thefts in San Francisco, we only had the points of the car thefts, but we had no idea as to how many cars were actually in those different locations. And as I mentioned at the time, everything else being the same, having more cars should yield more car thefts. So we really need to get a sense for what this population at risk is. And then we can use this rate or this proportion as an estimate for the underlying risk. It's really an estimate of a probability. And how we get this risk estimate, there are a number of different ways. The easiest concept is what is called a raw rate or a crude rate. And it's simply a proportion. It's simply the ratio of the number of events over the population at risk. And in practice, this is typically expressed in not as a proportion as such, but in something that is easier to understand, like number of events per 1,000 people or per 100,000 people or some multiple like that, which gives a better sense than an actual proportion. Say if the proportion is 0.0015, that doesn't really mean that much, but if you say that's 15 per 10,000, then it becomes much more concrete. And as it turns out, this very simple proportion or crude rate turns out to have some very desirable properties. As we'll see in a few minutes, it is unbiased, and it's also what is called the maximum likelihood estimate for the underlying risk. So what this means is that in the absence of other information, this is as good as we can do. So then our purpose is to assess the extent to which this risk is stable over space. And specifically, we want to assess the extent to which this is not the case, which we call spatial heterogeneity, when the risk is not uniform across the space. And specifically, we tend to be interested in identifying areas with elevated risk, higher risk than elsewhere, and then eventually, but we won't actually do that in this course, tie this elevated risk to some explanatory causal factors. But the purpose of risk mapping is to get an estimate, a good estimate of the underlying risk and be able to assess how it changes over space. And this is an illustration of of what a crude rate map does. So this is the data for the state of Illinois, for the counties in the state of Illinois for COVID in June 2020. And on the left, we have what is called a box map, which is an outlier map for the counties. And so we see on this map very high outliers, in fact, total 16 outliers, which are counties with extremely high number of cases. But let's focus for a second on this area within the black rectangle. So we have 2 counties with extremely high cases, counts, a spatially extensive variable. And then on the right, we have the population. And the population, we have in the same box several counties with very high populations, just the people, and then counties with much smaller population. The light, these blue ones are the first quartile. These are upper outliers, so they're outside the fence of the box plot. So what does this do for our rates? And this is to illustrate how misleading a map of simple counts can be. As you see in this example, the 2 counties that were outliers for the count variable, because they also had a large population, after you correct for that by computing the crude rate, they are no longer outliers at all. In fact, they are very much along the median of the observation. And so another striking effect is here in the Chicago metro area, which tends to have the counties with the largest number of people, the largest populations, and therefore everything else being the same, as I mentioned before, also the largest number of cases here. After you correct for the population, there's only 2 counties that remain outliers. The rest are high, but not extremely high. So that's the purpose of converting the spatially extensive variable of a count to a spatially intensive variable of a rate, and never make a map of counts. Okay, so we have this initial estimate of the underlying risk. How do we know whether this is high or low? Of course, we can do a box map as we just did, but this box map is relative. It's based on the ranking of all the rates, and as such, it doesn't tell you whether these values are truly extreme or just large relative to the others in the state. For example, if the rates in the state were super low, then an outlier would still be a pretty low value, a pretty low risk. So how can we get outside this relative mapping and get a better sense of what is really high and what is really low? And that is the notion of excess risk. And the notion of excess risk comes by comparison the risk in a particular location to some reference, to some standard. And what is this standard? Well, typically it's a reference group. So, for example, for the counties in the state of Illinois, it would be the rate for the state as a whole. That is not the average of the rates of the counties, but it is taking the state as a whole to compute a rate. So the average risk, and this is often confused, is not the average of the county rates, but it's all of the cases in the state divided by all of the population in the state. And more technically, this is actually an average of the county rates, but it's a weighted average, where counties are weighted by their population share. So obviously, the counties with more people will contribute more to the average for the state than the counties with fewer people. They should not be treated equally. So the average of the rates for the counties in the state treats each county as an equal contributor to the computation of the mean. But this is incorrect because it favors the small counties and lowers the importance of the large counties. So to get the reference rate, we take all the cases and all the population and compute a rate for that. And so a little more formally, if we say that the number of cases in a given county is O sub I, and the population at risk in that county is P sub I, then the rate, the crude rate or raw rate for each county, R sub I, is O sub I divided by P sub I. It's as simple as that. The average risk is the sum of all the cases, the sum over I of all the O sub I, over the sum of all the populations, the sum over I of all the P sub I. So now we have our average risk. How can we use that? We can use that to compute for each county how many cases we could expect if the average risk held. It's very simple. We take the population of the county and we multiply it by the average risk, which is the state risk. And that gives us E sub I, the expected number of cases that would have occurred in the state had the county followed the state average risk. So if the average risk in the state is 1 per 10,000, then if the county has 30,000 people, it would have 3 expected events. Now, what do we do with this? We compare this to the actual events. So if the actual number of events in our example, say, would be 6, 6 is higher than 3, so that's an excess risk. If it would be 1, 1 is less than 3, so that would be lowered risk. And this is how the excess risk calculation works. It's a relative number. We take the actual observed number of events, just as before, O sub I. We compute what the expected number of events would have been had the state average risk applied to that county, and then we take the ratio of the observed over the expected number of cases. This is the relative risk, also referred to as a standardized mortality rate in some literature. So it's a very simple concept. You compute what you would expect to see based on some reference average risk, and then you see what you actually have. If you have more, you're not doing so well. If you have less, you're doing better. So then, again, we're interested in mapping this, and we can express this visually in what I call an excess risk map. And in the excess risk map, we compare this ratio of observed over expected to the value of 1. What does that mean? If it was 1, it means that you get exactly what you can expect. So if you have more than 1, you have more events than on average. That's a higher risk. If you have less than 1, you have fewer events than expected. So you have a lesser risk. And now we can compute these ratios for each county and then map them. And then in the map, we can find places that have truly elevated risk. And for the case of COVID in June of 2020, we identify one county here with more than between 2 and 4 times the state average. At that time, there were still many counties in Illinois that had no cases at all, or very few cases, or had no deaths at all. But even in the case of the deaths, we find a particular county that has a rate of more than 2 times the average for the state. Whereas if we look at the Chicago metro area, there are several counties in the Chicago metro area that have fewer cases than the state average. And this is not something one would expect at first sight. So what is this good for? It's good for as an exploratory device to identify locations that somehow deviate a lot, because we are interested in rates that are 2-4 times higher than the reference, than the state average. So, of course, this doesn't explain anything. It identifies the interesting locations, but it doesn't explain why they are the way they are. Okay, so with the maps of the risks, an underlying assumption is that the precision of the estimate of the risk is the same everywhere. And this gets a little more statistical, a little more formal. The bottom line is that this is not true. So the problem with rates is that the variance of the rate is not constant, which is referred to as variance instability. So the crude rates, by construction, have a variance that is not stable across space. What does this really mean? This means that your estimate of your risk in some places is better than in other places, or to turn it around, in some places is much worse than in other places. So what do we do with this? When we look at a map, we tend to think that each location has the same precision. In the case of rates, that's not the case. So therefore, there is a way to correct the rates to kind of fix this problem of variance instability and make them more comparable to each other. And to get there, we need to do a little bit of math. First of all, we have to think about what these events are. So, for example, the COVID cases. You can think of the number of COVID cases in the population, let's say X cases in the population of P, as a draw from a binomial distribution. And you may remember the binomial distribution from your stats classes, where you have an urn with red balls and white balls, and you know the proportion of red balls. And then what is the probability that if you grab 5 balls, that 4 of them are red? Those kinds of probabilities are determined by a binomial distribution. And the binomial distribution has one important parameter, this pi here, which is the probability of the success of an event. So this is the risk that we're really interested in, but we don't know what it is. Given this risk, we can find out what is the probability of, given a population of 10,000 people, that we have 5 COVID cases, that we have 10 COVID cases. You can compute this all with this expression here, which is the familiar binomial distribution expression. So let's look at the moments of this distribution, specifically the mean and the variable. And you may have forgotten this, but the mean of a binomial distribution is the product of pi times the p. And in fact, if you recall, that's exactly the principle we applied to compute the expected number of cases. We applied a reference risk, the average for the state, to the population of the county. So you can think of the reference risk as being pi, and we apply that to the population. So the mean is pi times p, and the variance is pi times 1 minus pi times p. So both the mean and the variance depend on the population p. But this is the mean and the variance of the number of events. that's not the mean and the variance of the rate, because the rate is actually a ratio of the number of events over the population. The number of events is a random variable. The population is a constant, is fixed. So we call your basic math stat operations to get the mean, the expected value of the rate, is the mean of the numerator divided by p, because the rate is O over p. So we just saw that the mean of the number of events is pi times p divided by p gives us pi. That's a good thing, because this shows that this crude rate, simply the proportion, is actually a pretty good estimator for the underlying unknown risk. In fact, it's an unbiased estimator for the risk, because the expected value of the rate is exactly the underlying risk. So that's a good thing. For the variance, it's slightly complicated, slightly more complicated. So we still have the variance of the numerator, but now because it's a variance, we need to divide it by p squared. So that gives us pi, 1 minus pi times p over p squared. So the result is pi times 1 minus pi divided by p. And in a number of respects, this is a unconventional result. And in terms of what? So first of all, if you look at the numerator is a function of the mean. The mean is pi. So in a lot of distributions, you don't have that. The variance is totally separate from the mean. Here, the variance is actually a function of the mean. So that implies that if you have a larger value of pi, then your variance will be greater. So the variability of the estimate of the underlying risk depends on the magnitude of the risk. That's a non-standard feature, but it's not that serious. The second one is much more serious, is that the variance depends inversely on the population p. The p is in the denominator, as we see here, pi times 1 minus pi over p. And what this means is that if p is very large, your variance will be small. But by the same token, if p is very small, your variance will be much larger. And so the variance instability really means, the bottom line of it is, that small areas have very unreliable estimates of risk. And you might just think of it as an example. If you have in these smaller counties 0 cases of COVID, does that mean that the underlying risk is 0? Or does it mean that it's something above 0, but we just have a very imprecise estimate of that risk? It is, of course, the latter. So how do we deal with this? Because p is in the denominator, we know that small areas, and this is a small area estimator problem. You may have heard the term small area estimates. That's really what this is about. They have less precision. And just to give you a simple numerical example, say we knew that the underlying risk pi was 10%, 0.10. And we had 2 counties, one with a population of 500 and one with a population of 100,000. Then the small county would have a standard error of 0.013, but the large county would have a much smaller standard error of 0.0009. So the precision is inversely related to the size of the spatial unit. And that is a problem. So what are we going to do about this? We will transform the rate a little bit, and this is called rate smoothing. And it's particularly relevant in the field of disease mapping. So the rate estimates have variable reliability. They're less precise for small areas. So why should we trust them for small areas? That's a small area problem. In my example, If we have a small county with no events, does that mean the risk is zero? And here we take on a Bayesian perspective. Bayesian statistics is a whole framework for learning about the data and quantifying uncertainty. And in the Bayesian framework, an important principle is the principle of borrowing strength. So what this means in practice is that here we're stuck with a rate of zero, an estimate of zero. We are pretty sure that that is not the correct estimate of the underlying risk. How can we do better? We can do better by using additional information. What kind of information? The information about a reference rate. In the Bayesian lingo, that is called a prior. So this notion of borrowing strength from other information, in this case a reference rate, is the principle of shrinkage. We are shrinking our estimate towards some reference rate. And this shrinkage principle was spelled out formally by James and Stein in a very famous paper, and it has to do with the trade-off between bias and variance. So as we saw previously, the crude rate is as good as we can do in terms of bias. It is unbiased. The bias is zero. But it has a variance that is not very good. The variance is a function of inverse function of the population. So for small areas, the variance can be very large. So what we're going to do instead is move away from this unbiasedness and have a hopefully slightly biased new estimate that has a much smaller variance. So then the combination of the two, which is called the mean squared error, which consists of the part of the bias and part of the variance, we make the bias part from zero to something, and we shrink the variance part to a much smaller variance, so that the overall performance in terms of mean squared error is better. And specifically, for small areas, we will shrink the estimate, the crude rate, towards the reference value. And the way we do this is mathematically very complicated. I'm not going to go into the details, but basically it's a weighted average where the weight depends on the variance of the original estimate. So what does this mean? In practice, if you have a large area, it means nothing. Nothing changes. So if you have a large population, the variance will be small, and in the weighted average, all the weight will be on the original crude rate, the original estimate. But if we have a small area, then the variance will be large, the variance of the initial crude estimate. And so then the weighted average will favor the reference rate. So we are shrinking the estimate of the risk towards the reference rate. That is the effect for small areas. And there is a Bayesian logic for this. In practice and in our examples, we use empirical Bayesian Bayes smoothing. Why do we call it empirical Bayes? It all has to do with what this reference rate is. So in formal Bayesian statistics, the reference would have a prior distribution, which is a formal distribution like a beta distribution or a gamma distribution. But in empirical Bayes, the prior is estimated from the data. That's why it's called empirical. And in our examples, we use the average, in our case, the average for the state, as the reference rate. So we compute a new estimate as a weighted average of our crude rate, the R sub I, with a weight, and the reference rate, the theta, which is the state average, with the complement of the weight. And the weight is a function of the variance. So large variance, small weight, small variance, large weight. just to show you what this looks like, this is the rate, the death rate, the crude death rate for the COVID cases in June of 2020. So here, this is a little bit strange. This is a box map. And if you recall from the intro spatial data science, if we have a lot of zeros, which we do, then these different categories all get bumped up. So as a result, 77 counties get bumped into the third quartile. The first and the second quartile are empty. And then we have 14 outlying counties of the death rate. So this crude rate map is actually not very informative. First of all, it doesn't show the fact that there's so many zeros, and the transition from zero to a non-zero value is all lumped together with these 77 observations in the third quartile. But also it has a lot of outliers, and we know already that a lot of these outliers here are in counties with a large population where we have a small variance. On the other hand, we know that some of these counties right here in the south of the state actually have very small populations, so they have a large variance. But let's just focus on the counties in this yellow rectangle, and we see we have 3 outliers. After we carry out the empirical Bayes smoothing, there are no longer outliers. They're still in the upper quartile, but they're no longer outlier values. The other thing we see is that we have a much more graduated distribution, and now every quartile has the required number of observations in it. So we see much better the spread of values across the state after smoothing. We see the effect on the outliers. We go from 14 outliers to only 5 outliers. So what does this mean? What is the implication? The implication is that the crude rate, because of this variance instability, may falsely flag counties as outliers with very high rates, when in fact they're not really that high, but the estimate is not very precise. So we change the estimate by shrinking it towards the mean as an inverse function of the variance. So what is actually going on here? What's going on is that you can think of the county rates in a cumulative distribution. And so the observations that have zero cases, and therefore an estimate of the risk of 0, if they're in very small counties, they will move towards the overall mean. So they will actually go up from 0 to some non-zero value. If they're outliers, very extreme values, they get pulled down from the high outlying value towards the mean, and so they may no longer be outliers. On the other hand, since this is a reshuffling of the order of the rates, large counties with high rates that were not outliers can now be bumped above the fence in the distribution of the box plot and become outliers. So there is a reshuffling of the order of the observations of the rates, where the effect is largest on counties or areal units in general with a small population, with a small denominator in the risk calculation. The bottom line, the most important aspect of the rate smoothing, the empirical Bayes rate smoothing, is that spurious outliers are removed. So what's good about smoothing? Actually, smoothing is quite a topic of quite some debate. So what's good about it? You get better estimates in a mean square error sense, where we're adjusting for the problem of variance instability. We get true outliers, we get rid of spurious outliers, and so overall our estimate of the ranking of the observations is better in a mean squared error sense. So we're giving up the unbiasedness in favor of greater overall precision. That's the bottom line. On the contrary, there's a certain degree of arbitrariness in this. Even though it seems like it looks very objective, the choice of this reference rate, or in the Bayesian terminology, the choice of the prior, is not always unambiguous. And different methods and different priors will yield different results. So in some way, by picking the method, you can manipulate the results to some extent. So it's actually a topic of healthy debate. Some people really favor using the original data and then dealing with the variance instability in some other way. Once you smooth the data, you have really moved away from the original and created, in the view of some, an artifact that depends a lot on the method and on the reference rate. Just to give you an example. So we're working with, in our example, with counties in the state of Illinois. Should the reference rate be the average for the state, or should it be the average for the whole country? Well, depending on which one you pick, you will get different results. So that's where the debate is about the application of smoothing for rates. My perspective, as you should know by now, is not to take this at face value, but to carry out sensitivity analysis. So this kind of gave you a sense of how we approach an estimate of risk, of the underlying risk. We're interested in building a risk surface or a risk map to find locations with elevated risk, typically. And we saw that the crude rate is a pretty good estimate of that, but that it suffers from variance instability, and smoothing the rate deals with the variance instability. In the next lecture, we'll have a different way of dealing with the variance instability in the context of a local Moran statistic. See you then.